Okay, so good morning everyone. So today what we are going to do is we are going to look at communication complexity and how we can use communication complexity to give depth lower bound to circuits computing various problems. Okay, so in particular what we will do is we will look at very famous theorem due to Karchmer and Wigderson, who gave a tight connection between the communication complexity of protocol and the corresponding the depth lower bound of a corresponding circuit computing it. Okay, so we'll come to that. So first let's lay the groundwork for communication complexity. Let's just discuss the notations and the definitions. So okay, the communication problem corresponding to A or to the relation R, let's say it's a relation X cross Y cross Z. So suppose we have a relation over three sets X, Y and Z, X cross Y cross Z. So the corresponding communication problem is defined as follows. So Alice is given small x belonging to capital X and Bob is given y belong to capital Y and they need to output Z in capital Z such that X, Y, Z belongs to R, or report that no such Z exists. Okay, so we have two parties. We have Alice and we have Bob. So Alice has X, Bob has Y. Okay, and now they need to communicate. Okay, so they need to figure out. So of course Alice doesn't know what Y is and Bob doesn't know what X is. So they need to communicate bits among themselves and figure out a Z such that XYZ belongs to R, if such a Z exists. And if Z doesn't exist, they need to say such a Z doesn't exist. Now, how does the, yeah, so as I said, okay, so specific example is, if suppose that Z equal to GXY, then Alice and Bob computes the function G. Okay, so as I said, so they send bits to each other during the execution of the protocol, to be more precise. The in a given round, the bit sent depends on the input of the corresponding player and the bits communicated in earlier rounds. Okay. So basically, in the first round, let's say one of the two parties, let's say we start with Alice. So Alice sends a bit. So because it's the first round, so Alice's bit would only depend on the input of the corresponding player, that is Alice's input X. Now Bob will have the bit that he receives from Alice. Okay, so Bob will have his own input, that is Y, along with the bit that he receives from Alice. So the bit that Bob sends would depend on both these two. And then in the second round, the bit that is sent by Alice would depend on her input, which is X, and the bit that were transmitted in the earlier round. So this is how the communication proceeds. Okay. And okay. So now we define what is the communication complexity. So the communication complexity of a protocol pi for an or on an input x comma y, okay, we'll write that as C pi x comma y is equal to the total number of bits communicated to execute pi on the input xy. Okay, so for a given input xy, if Alice has x and Bob has y, what is the total number of bits that is communicated to generate the output is C pi xy. The communication complexity of a protocol pi, okay, so we define C of pi as the maximum communication complexity over all pairs of inputs. Okay, this is the standard way. And the communication complexity of a relation, okay, so suppose we have a relation R. So for a relation R, communication complexity of R is defined as the minimum over all protocols of C of pi such that pi computes R. Okay. So now we know what we mean by the communication complexity of a relation. So we will look at two types of relation, and in fact both are sort of similar. So we consider two types of relation. The first one is, so suppose we have sets A and B consisting of strings, consisting of n-bit strings such that A and B are disjoint. Okay. Now we define the relation R AB as all, so it tuples x, y, I such that x belongs to A, y belongs to B, and the ith bit of x is not equal to the ith bit of y. Okay. So suppose, so think of two sets. Suppose we have two sets that are disjoint, okay, which means that, well, there has to be some string that is different in both the sets. So we define well, and assume they are non-empty as well. So if they're empty, of course this is not true. Assume both A and B are non-empty. So there has to be some string in both A and B. So we define the relation RAB as follows. Okay, so it is all tuples of this form. So what is RAB? So RAB is basically a subset of X, or not X, so A cross B cross, the set consisting of 1 to n. Okay. The second type of relation that we define is what is more appropriate for us for a function. So let f be a Boolean function. F is a function from 0, 1 to the power n to 0, 1. So we define R of f as equal to R f inverse 0 comma f inverse 1. Okay. So basically if there is a protocol for R of f, it means that Alice is given a string which evaluates to 0, Bob is given a string which evaluates to 1, and they need to agree on an index on which both x and y differ. Okay. So this is roughly the framework that we would be considering. So let's look at an example. Okay. So consider the XOR function. Okay. So what is the XOR function? So you are given input string. So you are given, let's say, an input, and you output 1 if it has an odd number of ones and 0 if it has a even number of ones. So, it is the same as the parity function. So, now we will define a protocol. So, first of all we need to define what we mean by the corresponding communication problem here. So, we define the communication problem as follows. So, in the corresponding communication problem, Alice has X such that X1 parity up to Xn is equal to 0, and Bob has Y such that Y1 up to Yn is equal to 1. Okay, so both Alice and Bob have two strings. So, one way to, yeah, so because they must be of different, yeah, so this actually does not belong to Zoran and this belongs to Zoran, right? So, yeah, so Alice has this, and now they have to find out, they have to communicate among themselves, and they have to find out a bit on which X and Y differ. Okay, so how do they proceed? So, the idea is you apply a divide and conquer approach. Okay, so you kind of use the fact that, well, for example, if I have n bits, okay, whose parity is 0, then if I look at the first n by 2 bits, if the parity of the first n by 2 bits is 1, then the parity of the next n by 2 bits also has to be 1, and if the parity of the first n by 2 bits is 0, then the next n by 2 bits is 0, and if I have parity of n bits which is 1, then the opposite is true. So, basically if the first n by 2 bits is 0, then the next n by 2 bits must be 1 and vice versa. So, this is the principle on which the protocol is designed. Okay. So, here is the protocol. So, let us say that we have Alice who has X and Bob has Y. So, let us say Alice begins. So, if n is strictly greater than 1, compute A1 which is equal to the parity of the first n by 2 bits and send A1 to Bob. Okay. Now, what Bob does is Bob computes B1 which is equal to A1 parity Y1 up to Y n over 2 and send B1 to Alice. Okay. Now, if what is the condition? If B1 equals 1, then what should we do? What does it mean if B1 equals 1? Then they should recurse on the first half, right? You can actually check the case. Okay, so let us just look at one case, the other case is similar. So, suppose, so case 1 is, suppose let us say that A1 was equal to 1, which means that yeah, exactly, yeah. So if A1 is equal to 1, it means that the parity of the first half of Alice, the parity of first half of X is 1, and if the parity of the first half of X is 1, which means A1 is 1, then the parity of the first half of Bob must be 0, right. So therefore, if they recurs on the first half, then you have two inputs on which they differ, okay. So then recurs on first half, else recurs on second half, okay. And you do this, and now when do you stop? So you stop when, and what is the invariant that you are maintaining at each round? So the invariant that you are maintaining at each round is that the current string that you have, their parities differ. So that is the invariant, and of course in each round the size of the string gets halved. So stop the protocol when n is equal to 1. At this point, we, or Alice and Bob, have an index I such that the inputs are different. So basically the index at which they stop. Okay. So the protocol is simple. So what is the communication complexity of this protocol? So suppose let's give this a name. So let's call this as pi ZOR. So the communication complexity of pi ZOR is how much? How many rounds would there be? There is ceiling of log n rounds, and in each round we communicate 2 bits. So we have a total of 2 log n bits that are communicated maximum, okay, which means that well, the communication complexity of ZOR is at most 2 log n, or let me be a little bit more. So actually I'm not looking at exactly ZOR, but the relation corresponding to ZOR. Okay, so I haven't defined it formally, but you can define what is the relation corresponding to the ZOR function. So this is it, because there is a protocol, therefore it is at most 2 log n. Now what does this say? So we are looking at, so far we have been looking at communication complexity, but what does this say about the connection between the communication complexity of ZOR and circuit depth? In other words, why are we considering? So we have to kind of, so we have two different models. So we have two different frameworks. So one is I have a function, and the first framework is I have to design a circuit for that function, and I study the size, the depth of the circuit. The other is I have a function and I want to study if I look at communication problem corresponding to this function, what is the minimum number of bits in which that problem can be solved? What is the minimum communication complexity in which that problem can be solved? So these are the two frameworks. So now I want to study what is the connection between these two frameworks. To get to that, I have to define, right? So I have to define the relation, because for communication complexity, the way we have defined it, it is for a relation. So for a function, I have to define a relation. So this is, I mean, this is one way to do it. You can actually, well, any other way is actually the same. So now, what can we say about the, let's say, the minimum depth of a circuit computing XOR? Okay. So we are only looking at, okay, so for the purpose of this topic, we are only looking at bounded fan-in circuits. Okay, so let's say we are looking at circuits over AND or and NOT gates. Okay, so the question is, okay, let me also define one more term here. I think I have defined it earlier, but probably not. So let me do it. So for a Boolean function f, how do I write this? Let d of f denote the minimum depth of a circuit computing f over and or and NOT gate. So we assume these are gates whose fan-in is bounded by 2. Okay, so d of f is the minimum depth circuit that computes f. So what can we say about d of XOR? Well, it cannot order of, yeah, so it is log n, basically omega log n. Okay, so it is at least log n. Why is it at least log n? Kravchenko's theorem talks about the size. Well, that is one way to argue. So that is what is a more simpler explanation, much simpler. Let's say you don't use any theorem. So again, it is just pigeonhole principle that, well, if you have a circuit, exactly. So if you have a circuit whose depth is less than log n, which has bounded fan-in, then it must skip some input. It cannot depend on all inputs. If its depth is, let's say, small o of log n, right? So its depth must be log n, at least log n, so that it looks at all the inputs. And the parity function or the XOR function, it actually must look at all the inputs, because even if you skip one, I mean, even if you skip one bit of the input, the parity function can depend on that bit. So we know this. Okay. So what we have is that d of XOR is at least log n by this argument. Okay. So now what we have is that we have that the communication complexity of XOR is also this. So we kind of have connection in one direction. So what we will show is that not only does the communication complexity, well, yeah, it doesn't say. So this says it is at most log n, but well, it can be even smaller than log n. I mean, we still don't know whether this is a tight upper bound or not. What we will show next in the remaining part of this lecture is that this upper bound is actually tight. You cannot have communication complexity protocol which is smaller than log n. In fact, we will show the following general result. That So this is due to Karchmer and Wigderson, and I think this was 1980 probably. Yeah, 88. Okay. So for let f be a Boolean function, then what we have is that the communication complexity of the relation corresponding to f is equal to the depth of the smallest circuit that computes it. Okay. So this gives a tight bound on the well, whichever way you want to look at it. So suppose if I want to consider depth of circuit, so one way of studying depth is via the communication problem, the corresponding communication protocol. Okay. So how do we prove this theorem? So the proof is actually not very difficult. So, and as expected, it goes in two ways. So first we show that, well, given a circuit, okay, there is a communication protocol corresponding to that circuit, which has the same, I mean, whose the number of bits communicated is corresponds to the depth of that circuit, and the reverse. So given a protocol, there is a corresponding circuit. Okay. So first, let us prove the direction that okay, given a circuit, there is a communication protocol. So C R of f is at most D of f. So let C be a circuit computing f, and using De Morgan's theorem, we will assume the following. So assume that C does not have any NOT gates and all literals are at the leaf level. Okay, so well, if you have a NOT gate in an intermediate level, what we do is we apply De Morgan's and we keep on pushing it down, and then finally when we reach the very lowest level, we just replace the corresponding NOT gate with the, I mean, with the corresponding variable or its complement, whatever it is. Okay. So now we will show that, yeah, we'll show that there is a communication protocol for R of f, which communicates at most the depth of C many bits. Okay. So what is the idea? What is the idea of this problem? So the idea is as follows. So, well, what does Alice and Bob have? So we are looking at the relation R of f. So Alice has an input x which evaluates to 0. Bob has an input y which evaluates to 1. Right. Now they have to communicate among themselves and they have to produce, well, an index on which x and y differ. So the idea of the protocol is that Alice and Bob, they would in some sense agree on a path, okay, from the root all the way up to a literal, such that on that particular literal x and y differ. Okay. So Alice and Bob traverse along a path from root to a leaf of C such that at the leaf x and y differ. Moreover, so that is one thing. Moreover, it is not just any path, but it is a path which maintains this invariant. Okay. The path also maintains the invariant that Cv of x should not be equal to Cv of y for each node v in the path. Okay. So, before giving you the proof, actually it is easier to give the intuition. So, suppose I have a circuit. Okay, I start at the root. What do I know at the root by my input? So, what I know is that, well, okay, so what we have is, so Alice has, so let's write A. So, Alice has x and Bob has y. What else do we know? We know that f of x is what? F of x is 0 and f of y is 1. Which means that C of x must be 0 and C of x must be 1. So, the invariant is satisfied at the root. So, at the root I have the property that, so here I have the property that C of, well, x is, it is little more than saying not equal to, I have the property that C of x is equal to 0 and C of y is equal to 1. And let us say I will use the notation subscript to denote that which node I am looking at. Okay. So, CR of x is 0 means that at the root they evaluate to 0. So, this is what is given to us. Now, I have to find a path. Okay. So, Alice and Bob have to agree on a path. Now, let us say that from here there is, so both these nodes have 2 children. Okay. Now, if x and y disagree at the root, then what we have is that there must be one node, okay, there must be one child again on which x and y must disagree, and that would depend on what? That would depend on what kind of a gate R is, whether it is an AND gate or whether it is a OR gate. Okay. What do I have? So let us assume without loss of generality it is an AND gate. So, suppose if R is an AND gate, what can I say about x and y? So, CR of x is 0. If R is an AND gate, what does it say about the inputs to an AND gate which output 0? It can be anything, it can be that both are 0 or it can be one is 0 upon 1. what can we say about Y if R is an AND gate? Huh? If R is an AND gate, then for Y we can say something a little more stronger. Then what we must have is that both of these must be 1. Okay. Now what Alice does is, so suppose if R is an AND gate, then Alice would decide, well, which of these two is evaluating to 1. Okay. So Alice decides which of these two evaluates to 1, and then Alice would choose which node to go to. Okay, or well, not 1, which of these two evaluates to 0, because I have to maintain the invariant that C at the next level also they must be 0, and well, let's call them as, let's say, VL and VR. So let's say that they go to VL, then it must be the case that CVL of X is 0 and CVL of Y is 1. So if R is an AND gate, then it is clear that CVL of Y is also 1 and CVR of Y is also 1. But which of the two is 0 would would determine Alice whether Alice would want to go left or right, and that is what Alice would communicate to Bob. And this is the entire idea of the proof. Okay. Because CR of X is 0. It is meaning that on input X, what does C output, or the gate R output? So R is the root gate. So on input X, what does the circuit output? Because the circuit computes F, then on input X, it must output what F is. Okay. So this is just, I'm just overloading the definition, because I would like to use not just the output of a circuit, but the output at gates as well. That is why this subscript denotes the output of a circuit at a particular gate. So if again, so if it is if R is a OR gate, then it is just a symmetric argument. Okay. So if R is an OR gate, then what we have is that, well, if CR of X is 0, then both CVL of X must be 0 and CVR of X must be 0. Okay. So Alice doesn't have anything. Alice can go to either one. Okay. But then Bob has to decide which side Bob wants to go to. Okay. So if CR of Y is 1, it means that at least one of them has to be 1. So then Bob decides whether to go to VL or VR, depending on which side is 1. Okay. And that is essentially the protocol. So let me write the protocol. Okay. Or so let me just correct this a little bit, because the invariant that we maintain is, well, this is true, this is of course not false, but we actually maintain something stronger. So not just we maintain that CV of X is not equal to CV of Y, what we maintain is that at every node of the path, CV of X is equal to 0 and CV of Y is equal to 1 for each node V in the path. Okay, that is what. So it is true at the root, and then we'll show it is true at every intermediate node as well. So start at the root. So suppose, let me show this pictorially, this is easier. So suppose I have a node V with children VL and VR. Okay. So if V is a AND gate, then Alice sends 0 if CVL of x is equal to 0, and Alice sends 1 otherwise. Correspondingly, if V is a OR gate, Alice doesn't do anything, then Bob sends 0 if CVL of y is 1, and Bob sends 1 otherwise. Okay. Okay. So note we are doing exactly the same. So if V is an AND gate, then Bob doesn't has to decide. Alice basically decides which direction to go to. Okay, so Alice sending 0 means that Alice is telling that okay, go left now, and because at the left node, at the left child, that invariant is maintained, and if well the invariant is maintained at the right, then Alice sends 1, and Bob basically does the same thing. So if V is an OR gate, then Bob will maintain the invariant that Bob sends 0 if well the invariant is maintained at the left node, and Bob sends 1 otherwise. Now what do you do at the next step or at the next round? So if the bit sent is 0, then what do you do? If Alice or Bob send 0, then continue at VL, else at VR. So which direction you go to is determined by what bit is sent. Okay. Now it is let's and when do you stop? So you stop when, as I said, you have reached a leap. So stop when a leaf is reached at this point. We have by the induction hypothesis, we have a literal on which x and y differ. Okay. So proof, well, the proof is again simple. It is basically exactly what I have said so far. I will not write down the proof. Let me just give the sketch. You can complete it. So it follows by induction. Okay. So at so what is our induction hypothesis? So we maintain the so the induction is on the depth of the circuit, and the hypothesis that we maintain is that at node V at well, is it called depth or well, depth probably, yeah. At depth d, CV of x is 0 and CV of y is 1. Okay. So if V is the root node, then this is true by the assumption itself that C of x is not equal to C of y, because f of x is equal to 0 and f of y is equal to 1. So at V, if V is the root, then this is true by well, the definition that we have. Now suppose it is true at any node V, okay, if the induction hypothesis is true at V, show that it is true at either VL or VR. Okay. Now, how many bits are communicated? So I'll just leave this. So how many bits are communicated in this protocol? So the number of bits, so let's give a name to this protocol. So let's call this protocol as pi. So we have that the number of bits communicated in this protocol is at most the depth. Okay, whatever is the depth. Any questions? So again, the idea is actually very simple. So well, Alice and Bob, they kind of just try to find out which side they need to go to in order to maintain this invariant at every node of the path. That's all. And they can actually do this because because you, when you are at a current node, you already have this property. So therefore, it must be true at one of the two children. CV of x. Okay. So CV of x is, so C is a circuit. X is an input to that circuit. And suppose V is a node in that circuit, right? So
on that input, if we provide this X input to the
circuit, on that node V, what is it outputting? Yeah.
Sir, but the the total, the part which Alice and Bob has, the length of the input is half of the original circuit. And what is the input length for the circuit C? If it is N, then is the length
input length for the circuit. So Alice and Bob have X. Okay, so one more thing is that Alice and Bob have unlimited computational power. So both Alice and Bob have a copy of the circuit with themselves. They know what the circuit is.
Suppose there is the circuit C and the input length for the circuit is N. It takes
right, right, N. Right.
So and the X that Alice has.
Yes.
Is that X is of length N?
Yes. It is an input which evaluates to 0 on that circuit by definition. And Y is an input of length N again, which evaluates to 1 on that circuit. Okay. Where? No, we are not dividing. So in the process, so again, if you look at that XOR thing, okay, so we are looking at an input on which the function XOR evaluates to 0, another input on which the function XOR evaluates to 1. then during the protocol we are dividing that input in a appropriate manner. Yes.
Let's say it was and then L, let's say it was a odd, then accordingly as we described, let's say if it was and, then we saw that Alice would have to take the call on whether to go on left or right. But if it's a odd, then Bob has to take a call on whether it has to go left or right. So then if it's an and then at the next level it's a odd, then the first level, root level, Alice will take the decision, and at the second level, Bob will take it.
Yeah.
Just depends on like what the gate is.
Yes.
But the communication complexity problem, the goal is to find out the difference in bits.
Well, the way we defined, so we have defined this problem R of f, where we want to find out an index on which the two, I mean, on which x and y differ. So here, yes. So see, the communication complexity problem in general is what I said earlier. Okay, so you can think of it as we want to compute a function f which depends on two inputs, x and y. Now, Alice has one part of the input, Bob has another part of the input, and they want to compute f of x, y. Right, so f of x, y is the index I on which x and y differ. So we are defining f in that particular manner. Okay. Okay. So now let's look at the other direction. Other direction is also simple. So now we are given a here we have designed a protocol. So now given a protocol, we will design a circuit. So we will prove that d of f is less than or equal to c r of f. Okay. In fact, what we will show is something well, slightly stronger probably. So it suffices to prove the following. So we'll prove the lemma that if A and B are subsets of 0, 1 to the power n such that A and B do not intersect. Okay. And the communication complexity of R AB is at most D, then there exists a function f a Boolean function such that on entire A it goes to 0, on entire B the function goes to 1, and there is a circuit for this function of depth at most D. So what are we saying here? So take two sets. So here we are talking in terms of sets. So we have two sets which are disjoint, okay, some two subsets, and the communication complexity of this relation is at most D. Okay, so if Bob is given x belonging to A and Alice, if Alice is given an x belonging to A, Bob is given a y belonging to B, they can compute an index on which x and y differ in at most D bits. Now what this is saying is that there exists a function f such that f of A goes to 0, f of B goes to 1, and d of f is at most D. Okay. There is a circuit for F which has at most D depth. So, how does this, okay, so let's just spend a moment and understand that how does this lemma give us this inequality. Okay. So, first of all, if C of Rf is less than D implies D of F is less than D, then we get this identity, right? If C of Rf is smaller than a quantity D gives us that D of F is smaller than D, then it must be the case that D of F is less than CR of F, right? But how does this give us that C of Rf is less than D? How do we get? What does it mean to say that C of Rf is less than D? C of Rf is less than D if F inverse 0, if A were to be F inverse 0 and B were to be F inverse 1. But why is that true? Well, okay, let me put it slightly differently. So what I can do is, so let's say I'm given a function f. I want to compute CR of f, right? I want to find out what CR of f is. I can choose A to be F inverse 0. I can choose B to be F inverse 1. Then of course I get the hypothesis of this lemma that A intersection B is empty, and I get that, well, RAB is equal to, by definition, R of f. Okay, that is the definition of that. Okay, but then what this says is that there exists an f on which this happens. So that f need not be the same f that I started off with. It can be some other f prime now, right? So this is only saying that there exists an f on which this is true, D of f is true, but this can be some other f prime. What I need is that for the f that I started off here, I should have D of f less than D, but this can be some g. Okay, so
It is A and B are set. So what does it mean? What is the nature of this function which is acting on these sets? Like according to the notation.
which function? Oh, this one, yeah. This means that f of x is 0 for all x in A. Yeah. 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 So f of a set equal to 0 means for all inputs of that set it is mapped to 0, and the same thing here. So do you get the problem here? Okay. So again, so let me just to understand this in a better way. So instead of f here, just let me rewrite this as g. Okay, that I think will make it more clear, because f is a little bit we are using f in a different context. So there exists g such that this and d of g is at most d. Okay. So suppose if I start with a function f, okay, and I want to find out, I want to show that C of Rf is bounded or D of f is upper bounded by C of Rf. Now, if I want to apply this lemma, what I do is that I set A to be F inverse 0, I set B to be F inverse 1, I get the hypothesis that A intersection B is empty, and I get that, well, R of AB is the same as R of F. So therefore, CRF is at most D. But now what this is saying, that there exists a G on which this happens. Therefore, I get D of G is at most D. But what I actually need is D of F should be at most D. Exactly. So if there exists this G, then it must be the case that G is equal to F. Because by my definition, if, sorry, this should be G again. Yeah. G of A, G of B. So if by this thing, if there exists a G such that G of A is 0 and G of B is 0, it is actually matching with F. F of A is, we know that F of A is 0 and F of B is 0, and G of A is 0 and G of B is 0 implies that F is equal to G. So therefore, what we get is that D of F is also bounded by D. Okay. So therefore, proving this lemma would prove the result for us. Okay. So now let's look at the proof of this lemma, and that would complete the theorem. So the proof is by induction on D. So we start with d equal to 0. So if d is equal to 0, what does it say? So if d is equal to 0, then what we have is that C R A B equals 0, which means that Alice and Bob can compute the relation RAB without communicating any bit. What does that mean? What does that say about A and B? Huh? They cannot be the same, so they are disjoint. So they cannot be same.
For any pair in A cross B, that they differ among.
Exactly. So there exists an index I such that for every pair x comma y, x and y must differ on that particular index. So Alice and Bob, without actually communicating anything, they would just say I is the index. Okay. So there exists I such that for all x y belonging to A cross B, xi and yi differ. So which means that no matter what x Alice has and what y Bob has, they would just output I. They don't need to communicate anything. Now suppose the lemma is true for d minus 1. Okay. Now we have to prove it for d. So what do we have? Correct. We have to specify what g looks like, right? So we have to say what is the function g such that this happens. What would be the function g? So if there exists an I, then what would be the corresponding g?
Xi or Xi bar, this will depend on.
Okay. So then g is either xi or not of xi. Okay. Such that g of A becomes 0 and g of B becomes 1. Okay. Whatever it is, I mean, if the elements in A have it as xi, then well, it will be xi, and if the elements in A have it as a not of xi, then it will be again not of xi, whatever it is. Okay. Now suppose the lemma is true for d minus 1. That is, if CRAB is at most d minus 1, then there exists a g such that d of g is at most d minus 1. Okay. Then what can we say about d? Let pi be the protocol for RAB, okay, whatever is that protocol, let pi. And without loss of generality, suppose that Alice sends the first bit in this protocol. So either of the parties can send. Suppose it is Alice who is sending the first bit. Now, what happens to the, so if Alice is sending, so Alice, note that Alice has an element from A. So if Alice is sending a bit, what does that do to A? So what's, so what can be Alice's bit? So Alice's bit can either be 0 or 1. Okay. Now what does that 0, 1 do to the set A? So what it does is, it is partitioning that set into two parts. Okay, it is partitioning that set into an A0 and an A1, such that if that X was from A0, Alice would have sent a 0, and if that X was from A1, then Alice would have sent a 1. Okay. So this gives a partition of A as A equal to A1 union A2, A1 intersect A2 is empty, and if X belongs to, sorry, not, let me not write A1 and A2, let me write A0 and A1, A0 and A1, such that if X belongs to A0, Alice sends 0, and if X belongs to A1, Alice sends a 1. Okay. Now what do we have? So now we have actually broken down this relation into two sub-relation. Okay. So now we have, as a result, we get the following two relations R A1B and R A2B, right? So, and again, yeah, so R A1B and R A2B. And now if we consider the communication complexity of these two relations, CR A1B and CR A2B, what can we say? Well, now what we know is that, well, because already one bit is communicated, the communication complexity of these two relations is at most d minus 1. What else can we say? Well, we have to make sure that the hypothesis is satisfied. So this part is satisfied. A and B are of, so A1 and A2 and B are of course subsets of 0, 1 to the power n, that is clear. We also have that A1 intersect B is empty and A2 intersect B is empty, because A1 and A2 are subsets of A. So therefore, what do we get? So because it is for d minus 1, by induction hypothesis, what we have is, there exist G1 and G2 such that, let's look at G1 first. G1 of A1 is equal to 0, G1 of B is equal to 1, and D of G1 is at most d minus 1. similarly G2 of a I'm sorry, again I think I've confused it. So it is A0 A1, so it should be A0 A1 here, A0 A1 A0 A1 A0 A1. Okay, and let me write this also as G0 and G1. So G0 of A0 is 0, G0 of B is 1, and G0 of D of G0 is at most D minus 1. Similarly, G1 of A1 is 0, G1 of B is 1, and D of G1 is at most D minus 1. Okay. Now, how do we get, what we have to show is that the claim is true for D now. So, using this G1 and G2, how can I build a G for such that D of G is at most D? How do I define G now? Y and
A is going to be like any element of A is going to be 0 either for G0 or for G1, and any element of B is going to be 1 for both of them.
right. Exactly. So, we define G to be AND of G0 and G1 because now any element, so now if I look at G of A, so any element in A must belong to either A0 or A1. So therefore, by this if I look at the AND of both these zeros, so therefore on any element of A, G also must evaluate to 0 now, and because B is anyway the same, B is not changing, so therefore it is clearly true over there. And now what is the depth of G? So then what we have is G of A is now equal to 0 and G of B is equal to 1. So G of B is equal to 1 because already G0B and G1 of B were equal to 1, and the depth of this function G was whatever was the depth of G0 and G1, which was at most D minus 1 plus one more level. So it is at most D. Okay. Now this entire thing was when Alice had sent the first bit. Okay, what if Bob had sent the first bit? Okay, so if Bob sends the first bit, then so if Bob sends the first bit, what do we do? How? What? I mean, what exactly? Yes, it is symmetric, but what exactly do you need to do? So now instead of A, B is actually getting split because Bob is who, it is Bob who is taking the decision. So B gets split. So we have a partition of B into B0, B1. So everything is the same here. So now if X belongs to B0, Bob sends a 0, else Bob sends a 1. And finally, the function G that you compute will be G0 or G1. Okay, so if Bob sends the first bit, then B gets partitioned and finally G will be equal to G0 or G1. Okay. And that completes the proof of the lemma. Okay, so this also completes a proof of Karchmer-Wigderson's theorem, which shows us a tight bound, so which gives a tight bound on the depth of a bounded Fanon circuit over and or not, computing a function in terms of the corresponding communication problem, in terms of the communication complexity of the corresponding communication problem. Okay. So we will see some applications and some more stuff about communication complexity in the next lecture. So that's it for today.